Alright, so in the previous video I didn't realize that the bottom part was cut, but what you should know is from this I had shown that you factorize the common factor, and what remains is this x and that x bar, which now forms another bracket. It's the same term that we are multiplying um, itself with. So you will get x minus x bar squared. You will recall from the formula for variance that this is an integral component for the formula for variance. If we adjust it for degrees of freedom, then we have our variance. But what I want to do now is to talk about regression. Now we understand something about correlation. We understand something about covariance. So now we want to talk about regression. Now, if you have a set of data, let's say now this is your data, this is your wage, this is your education, using the example we were working with yesterday. Let's say these wages are expressed in thousands, so 0.5, 3, 8, 10, 18.5, 22.5, 29. No education, 7 years of education, 11 years of education, 12 years of education, 15 years of education, 16 years of education, 18 years of education. Now, you want to fit a regression line to this data in such a way that the distance between these observations and the line throughout is minimized, because the distance between each observation and the line represents the predicted error. Now, here is the challenge. We can try any line that you fit, for example, will satisfy several assumptions, but there is only one unique line that will satisfy every other assumption that we want to meet in regression analysis. Let's start with the simplest of them, is that if you add the predicted errors, they should always give you 0. So any line that you fit, the predicted errors, the sum of the predicted errors will always be 0. So now it doesn't satisfy us that much. We need something that will minimize the residuals or minimize the various errors from the sum of the errors from squared errors from the regression line. So what econometricians settled on years ago is a method called ordinary least squares method. So in short, it's called OLS. Now, our regression for wages, which we are calling Y, and for education, which we are calling X, would look like something like this. Y is equal to, let's use some Greek letters here, beta 0 plus beta 1x plus an error. where, or rather a disturbance term, where this disturbance term here is a random variable, where this disturbance term has a mean of 0, has a variance that is constant across all observations and so forth. Now, this one would be an example of a population regression function. Now, this is what is to be explained. Okay, it is what we observe. That's what we are observing in the data set before us. This here is what has been explained by the model, and this here is what the model failed to explain. Okay, so your regression line is divided into this. You can pretty much understand it in terms of these three components. But now, because it's very difficult for us to observe population data for, say, the labor market, the best we can do is to work with a sample of people participating in a particular labor market. So we can rewrite this in sample terms. Our yi will be equal to a beta 0 we are going to estimate using the sample, a beta 1 xi we are going to estimate from the sample, and there will be a predicted error for each observation. Now, what this tells you then is that our yi is actually equal to this component here is your predicted y. So this particular yet you're seeing means it's something that has to be estimated from the sample. This is your predicted y plus your mu I. Now, the method of ordinary least squares requires that we minimize the squared residual sum of squares, which means we need to square this number and sum it across the 7 observations. The answer we get is called the residual sum of squares. Now we can rearrange this into mu hat I is equal to, we take this to the other side, becomes yi minus y hat I. Right? So we need to square this, we square that, and we also square this. Then we are required to sum both sides. So we sum mu I squared is equal to the sum of yi minus y hat I squared. So the method that will give us values of beta naught and beta 1 hat that fit the best regression line is called the ordinary least squares method. What we have to do here, we have to apply the method of calculus to be able to get the formulas for getting beta naught and beta 1. So we can rewrite this as mu hat I squared is equal to sum of yi minus, what is mu hat I? we know that it is this part here, so we can put beta 0 minus beta hat 1 xi, and we square it. As you can see, the only things that are unknown in this expression are beta 0 and beta 1. We know x because that's the data we have. We know y because that's the data we have. Do you see that? And of course, the residuals are generated by that relationship we would have estimated. So the method of calculus requires us to do some partial differentiation. If you didn't do maths in high school, you just have to bear with us, but I think you'll be able to cope. So we have to differentiate these residual sum of squares with respect to each of these unknowns, and we do that in terms. So we first do it with respect to beta naught. Now, because the expression to the right hand, which is beta naught, has a power outside, so we differentiate first the power. So you bring the power down here, and you multiply that power by this entire expression, leaving the power. So that's yi minus beta hat 0 minus beta hat 1 xi. Then next, you differentiate everything in here with respect to beta naught. Now, this becomes 0 because this yi doesn't have beta naught with it. This also becomes 0 because it doesn't have beta naught with it. The only place where we have beta naught is here. So if we differentiate beta naught with respect to beta naught, we will just get 1. But there's a minus sign there, so we actually get minus 1. That's the number we get. Okay? Now, from methods of calculus, what we are actually doing there is almost as it were. For us to be able then to solve and get our beta naught, we must set this condition equal to 0. Okay? So we simplify this expression and set it to 0. Actually, this expression, this minus 1 is multiplying that 2, so it's actually minus 2 sum of yi minus beta hat 0 minus beta hat 1 xi is equal to 0. And you can divide both sides by minus 2 so that eventually you are left with sum of yi minus beta hat naught minus beta hat 1 xi is equal to 0. This is called a normal equation. Okay? Never mind about the word normal. It has its own origins which you don't have to know. But you should know that that's the technical name that equation is given. It's called a normal equation. Now, if we solve this normal equation, we will get the formula for beta 0. Now, because you got several terms here that there is subtraction in the brackets, we can distribute the summation sign to this term, to that term, to that term, and solve for beta 0. So that expression there, your sum yi minus beta hat naught minus beta hat 1 xi can be rewritten as sum of equal to 0, sum of yi minus sum of beta hat naught minus sum of beta hat 1 xi, and all this you set to 0. Now, because this is constant, what is going to happen is when you sum it n times, we are summing up to n times, it becomes n beta 0, okay? So then that means this entire expression here is now sum of yi minus, you are summing a constant n times, that becomes n beta 0, minus, we can take this constant outside the summation sign and leave the sum to be with x only, and we say this entire expression must be 0. So mathematically, to find beta 0, we have to make this term with beta 0 subject of the formula. So we end up having n beta at 0. You take it to the other side of the equation, and you remain with sum y minus beta at 1 sum xi. Now, you are set to find your beta at naught now. To remain with this only, now you have to divide both sides by n. So n over n beta at 0 is equal to sum of yi over n minus beta at 1 sum of xi over n. That cancels that, and you remain with the beta at 0. From our previous video, the summation of y over n is actually y bar, and the summation of xi over n is x bar, beta at 1 x bar. This is the formula for finding beta naught. So if I know beta 1, and these two I get them from the sample, I can estimate beta naught by just plugging beta 1 by the mean of x subtracted from the mean of y. That's how you get your estimator for beta naught. Okay, the formula we use to estimate that. Then, so we can do the same with respect to beta 1. So we said we have some mu I squared is equal to sum yi minus beta naught at minus 1 xi squared. So we have done the differentiation with respect to beta naught. Now we are going to do it with respect to beta 1 hat. So now we are going to do partial differentiation of mu I hat squared over d beta 1. Because there's a power, we first differentiate the power. So we bring the power here and we multiply it by the rest of the expression. Minus beta at 0 minus beta at 1 xi. Then, in the next stage, we differentiate what we see in the brackets here with respect to beta 1. Everything that doesn't have beta 1 becomes a 0 in that process, and we remain with this. So if we differentiate this expression with respect to beta 1, so this becomes 1 because differentiating beta 1 with respect to beta 1 is 1. And that 1 is multiplying the x, and there's a minus there. So we have a minus xi. And we must set this equal to 0. Now, we can take this minus sign and bring it here. All these things are multiplying each other, so it doesn't matter whether the minus sign comes here or you put it there, you put it anywhere else, respecting the brackets and so forth. So this is minus 2 sum of yi minus beta hat 0 minus beta hat 1 xi times xi equal to 0. So we can divide both sides, that is by minus 2, and divide your 0 by minus 2. What you get is the sum of yi minus beta hat 0 minus beta hat 1 xi by xi is equal to 0. This is your normal equation 2. It helps us find this slope parameter, estimate this slope parameter. Okay? So, from what we have done so far, we already know how to find beta hat naught, because we have a system of simultaneous equations here. So we can use the method of substitution. In this expression, we can put y bar minus beta hat 1 x bar in place of beta naught, so that everything is now in terms of y and x and beta hat 1. Beta hat naught is eliminated by this process of substitution. So then it means our sum yi minus beta hat 0 minus beta hat 1 xi by xi can be rewritten as sum of yi minus, here, let me first use a bracket so that you can see what I'm doing, minus beta hat 1 x bar, right, then minus beta 1 hat xi, right, everything by xi, and this should be set equal to 0. Okay, we can now simplify that by breaking this bracket so that we actually have yi minus y bar plus beta hat 1 x bar minus beta hat 1 xi, everything by xi, and this should be equal to 0. As you can see, we can do some rearrangements inside the bracket there and factorize. I see here there's beta 1, there's beta 1, so I can factorize, and here I have terms in y only, so this can be written as sum of, and I can open my corner bracket, yi minus y bar is one component of this, and so I want my xi to subtract my x bar, so I'm going to factor out minus beta hat 1, and in doing so, it means that we now have minus and we now have a plus there, so we'll start by x and end by x bar, like that, and then we close brackets, we have our xi outside, and we say this is equal to 0. Now what you observe is we can easily rearrange this. We are almost there. Please don't faint. So now what we have there is we can now distribute the summation sign while we are also multiplying everything in here by x, or we can start by multiplying by x just to make life easy. So we have y minus y bar. If we expand this bracket, so we are bringing this xi to multiply all the components in here, we will have xi here, then we will have minus beta hat 1 xi minus x bar by xi equal to 0. Then we can distribute this summation sign so that we have sum yi minus y bar by xi minus beta hat 1 xi minus x bar by xi is equal to 0. We want to find a formula for beta hat 1, so everything here that is beta hat 1 must go the other side of the equation. And starting to write that, I have beta hat 1. Where is my summation sign? Sum xi minus x bar by xi is equal to the sum of yi minus y bar by xi. Right? So for me to get beta hat 1, I have to divide both sides by this expression here. So then it means my beta hat 1 is actually equal to the sum of yi minus y bar by xi over the sum of xi minus x bar by xi. Now there's something, if you remember one of the results that we had in the previous session, we had something like this. One of the results which you have to recall, I think we had sum of x minus x bar by x by y. We showed that this will give us x minus x bar by y minus y bar. I think you remember that. And we showed that x minus x bar by x will give us x minus x bar squared. You remember that? Now, if we play around those results here, you will see what we will get. This entire thing will become sum of yi minus y bar xi minus x bar using the same. If I put y and x there, I would still get that. Okay? And then we are dividing that here using this result, sum of xi minus x bar squared. Now, this particular relationship helps us realize the link between regression, covariance, and correlation. You remember when I started, I told you that these three concepts are central. If you understand those three concepts and their interrelationships, then you are home and dry in this particular course. Now, if we multiply this expression by 1, where we think of this one as 1 over n minus 1 divided by another 1 over n minus 1. Okay? Up there you have sum of y minus y bar x minus x bar. I've omitted the I there, but just to save space, but know that it's there all the time. X minus x bar squared, right? So this 1 over n minus 1 cancels that 1 over n minus 1. That's what I mean by multiplying by 1. We haven't changed anything. What you have there is the same as what you have here. Now, this expression you have here is your covariance. Do you see that? Your covariance is the sum of the product of these deviations of y from its mean, x from its mean divided by n minus 1. So actually, this is covariance of x and y. But this here below is the variance of x. You see that? Variance of x. So it means that my beta hat 1 is equal to covariance of x, y over variance of x. So if I'm just given the covariance of x and y, and I'm given the variance of x, and I'm asked this question, tell me, what is the effect of x on y? What's the size of the effect? I just have to divide the covariance of x and y by the variance of x. The answer I get there is an estimate of this slope parameter, which measures the effect of x on y. Do you see that?